In this video, we are going to tackle the problem of what is called an ambiguous SSA triangle. An ambiguous SSA triangle is an SSA triangle problem where when you're trying to calculate one of the angles using law of sines, that angle that you're trying to calculate might actually be larger than 90 degrees. And so it may or may not actually be possible to find the value of the angle by using arcsine. So that's what we're going to be considering today, ambiguous case SSA triangle problems and how to deal with that issue. So the setting is this. We are given data about an angle alpha equals 30. The opposing side is A equals 5, and one of the adjacent sides is B equals 9. Now let's quickly compare this with the very similar exercise that we did yesterday. In yesterday's very similar exercise, the value of A was equal to 10. Because the value of A was larger than the value of B, we could be guaranteed in this problem that B was definitely not the largest side in the triangle. Because B was guaranteed not to be equal to the largest side, beta was guaranteed not to be obtuse. Beta was guaranteed to be less than 90 degrees, and therefore it was safe to calculate beta by setting beta equal to arcsine of something. In this problem, we no longer have that guarantee. The side labeled A is much smaller than B is. So the odds are quite good that B is the largest side in this triangle. Potentially, C is something like 7, for example, which would make B the largest side. B could be the largest side, which means that beta very well could be larger than 90 degrees. So, since beta could be larger than 90 degrees, it's possible that if I try to find beta by setting it equal to arcsine of something, this could be wrong. Because arcsine is always less than 90 degrees, beta could be larger than 90 degrees. So let's figure out how we would deal with a situation like this one, trying to use law of sines to solve a triangle problem where one of the angles that you need to calculate to make headway in the problem could be obtuse. So what I'm going to do is I'm going to start by setting up law of sines in basically the only way that I can. Sine of beta over the side length B, which is 9, equals sine of alpha, alpha being 30, and the corresponding side length is 5. So therefore, sine of beta is some angle at which sine outputs the value 9 times sine 30 over 5. Looks like beta is some angle at which sine outputs the value 0.9. So considering the unit circle for a minute, good old unit circle, we're considering angles at which sine outputs a value of 0.9. So it looks like there are two such angles. One of the angles is less than 90 degrees, and this is the value that would be produced by arcsine. Arcsine of 0.9, which is equal to approximately 64.16 degrees. But that's not the only angle at which sine outputs this value. There is a second angle larger than 90 degrees, which would also correspond to the same y coordinate on this circle, and that's the one on the far left, which, using the exact same reasoning that we used when we were solving trig equations, can be found by taking half a rotation, or 180 degrees, and subtracting the 64.16. So that would be the angle, the obtuse angle, 115.84 degrees. So the question is, what is the true value of beta? Is beta equal truly to 64.16 degrees? Or is beta equal to 115.84 degrees? The answer actually is both. There are two different triangles which satisfy the given information. I found a pretty cool tool online to actually visualize this situation. So we were given data about angle alpha, here represented by capital A. Alpha equals 30 degrees. And we were given information about the length of the opposite side, which was A equals 5, and the length of one of the adjacent sides. In this picture, it's just being represented in the top left, which would force beta, here represented by a capital B, to live in the bottom right. The graph is showing that there are two different triangles that satisfy this given data here. The first triangle corresponds to when the opposite side A is slanted here toward the bottom left. The second triangle corresponds to when the opposite side A is slanted here toward the bottom right. So there are two triangles satisfying the given data. One where the angle opposed to B equals 9 is obtuse, and one where it's not. So in situations like this, where you have two triangles that satisfy the given data, two values of beta that are legitimate solutions to sine of beta equals 0.9, there are now two triangles whose data you have to fill out. So in triangle number 1, the value of beta is equal to 64.16 degrees. And in triangle number 2, the value of beta is equal to 115.84 degrees. Let's find the value of gamma and of C in each of those cases. Now, to find the value of gamma, all you need to do is take 180 degrees and remove the given value of alpha and the calculated value of beta. So in triangle number 1, the value of gamma is 85.84 degrees, whereas in triangle number 2, the value of gamma is 34.16 degrees. In triangle number 1, we can use law of sines to determine the value of the side length C, to say that sine of gamma divided by C is equal to, one option would be sine of alpha divided by A. So if I reciprocate both sides, which will move the side lengths to the top and the sines to the bottom, then the value of C in this case would be 5 times sine of gamma divided by sine of alpha. And according to the calculator, the value of C in triangle number 1 is approximately 9.97. Whereas in triangle number 2, the calculation would be very similar, except that the value of gamma is different in this triangle, the value of gamma here is only 34.16. So because the angle is smaller, the side length will be smaller as well. This one is only 5.62. So two triangles satisfying the given data. Now in summary, when you're working on an SSA triangle problem using the law of sines, this is my recommendation. If it is possible, use the law of sines to find the angle corresponding to the smallest side length that you were given. This is what occurred back in video 18 in the exercise given here. In this exercise, we used law of sines to find the value of beta, which corresponded to the side length of 9, which was the smallest side length that was given to me. If you are able to do this, then guaranteed there are not going to be two triangles, there's only going to be one triangle, and guaranteed the value of beta is going to be equal to arcsine of whatever number you got from your calculation. However, if it is not possible to find the angle of the smaller side, if you have to find the angle of the larger side, then you have to remember that the angle might be larger than 180 degrees. And so the trick to use is to remember that if an angle, maybe call it theta, is a solution to sine of theta equals number, then so is the secondary angle pi minus theta. For example, in this exercise, we were trying to find angles that satisfied the equation sine of beta equals 0.9. Now, one of the solutions to that equation was equal to the output of arcsine of 0.9. But there was a second angle which made this equation true, and that was this angle over here in quadrant number 2, this obtuse angle of 180 degrees take away 64.16. So write down those two solutions to sine of angle equals number and check to see if both of these angles can be used to create a triangle that could exist in the real world. For example, here both beta equals 64.16 degrees and beta equals 115.84 degrees. Using both of those angles, I was able to fill in the values of gamma and of c without running into any mathematical impossibilities. Just to give you an example of a situation where the data that you were given corresponds to a triangle that cannot exist, let's consider the following situation. Here we have alpha equals 30 and b equals 9, but this time a is much smaller even than before. A is equal to 3. So in this case, if I tried to set up sine of beta over b equals sine of 30 degrees over a, then I get sine of beta equals 9 times sine 30 degrees over 3 units, and the decimal approximation for that is equal to 1.5. So this is a situation where I'm asking sine to output a value of 1.5, and so this is not possible. And so this data of alpha equals 30, b equals 9, and a equals 3 does not describe a legitimate triangle. There is no triangle that satisfies this data, because as I was trying to fill in the blanks of this triangle, I ran across something that is mathematically impossible. Another way that you might end up with an impossible triangle is if you were given something like A equals 40 degrees and beta is equal to 170 degrees, right? In this case, if you try to find gamma, then gamma, because of how big alpha and beta are, this would end up being a negative number. And for angles inside triangles, this is impossible. Law of sines is the perfect tool for solving triangles of the variety AAS. Solving it, we saw yesterday that using it to solve SAS triangles was not possible with law of sines. And SAS triangles could be tricky. Tomorrow, what we will introduce is the law of cosines, which is used to solve SSS and SAS triangles, neither of which are possible using law of sines only.